First of all, I'd like to thank the organizers for the kind invitation. It's a really nice place for the first time here and a very well organized conference. It works, right? Yeah, okay, good. Okay, and then, well, my talk will be about biomedical imaging. Let me start by saying there is really no modern biology and medicine without imaging. Yeah? Basically, I will talk about some typical challenges and then give some example problems and share with you some of solutions or potential solutions. Mostly, I will talk about our own research work. And okay, today there is also always some need to talk about machine learning. I will do exactly the same from the perspective of biomedical imaging. And finally, I will try to give some future outlook from one particular perspective. And you all know different medical imaging modalities, like you see here. We know from the literature there are a high number of different algorithms for different problems, and given that, we can realize wonderful applications. Yeah? And there is, I think, probably some misunderstanding about biomedical image analysis. And I guess some people, or probably many people, think it's just an application of all the wonderful methods we know from image analysis to solve biomedical imaging problems, application of existing algorithms. But this is not really true. Indeed, we see quite a lot of novel problems. I will go through some of them, rising from this field. And then, when we need novel algorithms in order to solve the biomedical problems in a better way. Okay. So there are specific challenges in this field that require specific solutions. And I like to share with you some of the challenges. They are in some sense general, in other sense also a little bit my personal view of the story. So we will see the constancy modeling for motion analysis, noise modeling, and so on and so forth. I will briefly go through all the challenges and say some words about some potential solution. And one very interesting observation here is you can find in literature many methods that work very, very well for normal images, but not for images from patients. But this is particularly the kind of images we are interested in, basically. So, yeah. Mm-hmm. And this is somehow related to database design. Every benchmark database should contain a sufficient portion of abnormal images, of different kinds. Yeah. And okay, let me start with this topic, motion analysis. Motion can be done in different ways. One is registration, the other is optical flow. Here you see, you see 2D optical flow fields and 3D optical fields for two different modalities. I will come back to the modality data. The issue here is, for motion analysis, let's say, here there's very frequently used assumption. It's so-called intensity constancy. It's a very simple one. Basically, it means despite of motion, the intensity or color doesn't change. You see here at position x, y, at time t, you have this intensity. At the next time, it moves to x plus u, y plus v, the intensity remains more or less constant, because we need some constraints to solve the mathematically imposed problem. And this is widely assumed in literature, but it can easily be shown that it does not apply to several imaging modalities. I will show you, I think, at least one or two such situations. Look at this very abstract situation. We have two images, template, reference. We like to do a motion analysis to register one of them to the other. Yeah? Registration motion means for each point, you like to find out the corresponding point in the next image. Yeah? Okay, let's try to find a corresponding point for this one. Where it is? Somewhere here, perhaps, but you see a problem. All the points here in this very dark ring, they are very dark. And all the points here in the dark ring, they are dark, not so dark. Yeah? It means there is some motion, but there is also some change of intensity values. This is called by the physical principles used in different devices. So it means, this fact simply means, if we do motion analysis in this situation, we need two things at the same time. We need to determine the movement of the position, and also we need to determine the intensity change at the same time in one single process, the so-called intensity modulation. Yeah? It's something beyond the typical motion analysis. But as I said, we do need some constraint. Otherwise, we will not be able to solve the mathematically e-pose problem behind it. So it means if we have to forget this constraint or intensity constancy, we need something else. So one potential solution is here. It means, well, each pixel may change its intensity, but the sum of all intensity values in one image remains a constant. There is indeed, in case of some physical measurements, very straightforward interpretation. In case of PET imaging, it means the radioactivity, which is injected in the body of the patient, cannot escape during the measurement, unfortunately. This is not good for the patient, but necessary, simply necessary. But this gives us a global constraint in order to solve problem. And one way of motion analysis, as said, registration. The idea here is very simple, at least theoretically. You have the template, you look for some transformation y, and then you compare the transformed template with some reference. This is a difference function. The difference between the reference and the transformed template. Then you try to find a transformation so that this difference is minimized. And in this case, we typically need a regularization to make the problem solvable. But in case of the mass preserving, we need to develop a step more. We need to extend this formulation, and we have developed the so-called Vampire algorithm for doing that. And as for the motion analysis, as said, there are two forms, registration or optical flow. In some cases, you can apply both. And indeed, taking the same constraint here, mass preserving, we also have developed a method for optical flow. Somehow it's blocked. Okay. And I will do not go into any detail. But the point here is, this is much faster than the registration. Actually, our experience here is, indeed, they show the two approaches for optical flow and for registration. They do show relative similar results. Actually, this optical flow solution will be built in the next generation of PET by Siemens. We did it in a very close collaboration with Siemens, and well, our code was not optimized at all, but they optimized our code in different aspects and plan to build it into the next generation device. But for what? For what kind of application? Here you see the potential application. Oh, yeah, okay. Yeah, okay. The motion is very slow here. it's related to the motion correction in PET device. One particular aspect of PET is it takes a long time, typically 10 minutes, 20 minutes. And in that case, the patient is somehow in this form. No global body motion, that's fine, but the patient is alive. The heart is beating logically, right? So there's some heart movement here, and this leads to this kind of measurement. This is quite typical. With the enlarged measure of the heart, and the shape of the heart wall is much thicker than it really is. And we have applied this kind of motion detection to find out the different, the motion between the different stages. Unfortunately, it's somehow, I don't know why. And here, basically, during the 20 minutes, there is a motion, heart beating, and then we try to find the motion between the heart beating phases and correct it. And finally, we can provide this motion-corrected measurement. And this is a motion correction to be built into the next generation of Siemens for PET device. And now I come to the second issue, noise modeling. So you see here the quite popular modeling. You have unbiased perfect signal. You have some additive noise source, mostly modeled by Gaussian. There are some reasons why Gaussian is so popular. But on the other hand, you see here, Gaussian model is not suitable indeed in some situations, probably in many situations. And for instance, here, in PET device, and here also in this remote sensing device, and you see what's the difference? The difference here, the noise part also depends on the signal U. So this is kind of signal-dependent noise. And what makes it difficult is here you see the additive noise, and you see the signal-dependent. In case of high signal levels, the distortion will become much higher. Yeah? It's a terrible distortion process. And if you compare the Gaussian noise here with Poisson or speckle noise typically visible in ultrasound, you will see this kind of signal should be more difficult to deal with than such normally distributed noise. And this is reflected in segmentation, in motion analysis. In case of optical flow instance, I have shown you this very simple assumption typically used, and indeed, in case of an ultrasound, we are faced with this signal-dependent model. You see again, this noise part is dependent of the signal. Yeah? So in this case, it can easily be shown that the intensity constancy does not apply anymore. And fortunately, we can replace it again with something else called, you see here, the individual intensity will change, but the distribution of the intensity values in a small neighborhood, it will remain constant. And we just use this constraint and develop an optical flow algorithm. And we could show that with this improved algorithm, we could achieve, depends on the signal images, 20 to probably 70% improvement of the optical flow computation. Yeah? And so the noise modeling does not only influence motion analysis, it also influences segmentation. And recently, we have done a literature review checking the segmentation methods which consider noise model inside. And there are not so many. And many of such methods, they are limited to some particular noise model, not a general consideration. Yeah? And we were working on general models. These are two methods from my lab, and they consider general noise models. And in one case, we do need the mathematical definition of the model. In the other case, we even do not need to know the exact model of the noise. Yeah? And why this is useful, this is just one example here. You see an ultrasound image, and you see the labeling from two physicians here, and they differ a little bit. Actually, they may differ even more. Yeah? And here you see, if we apply the Gaussian Morse model for the segmentation, the result never becomes reasonable. Yeah? But if we apply this is the correct noise model for ultrasound device, then we are indeed able to get a much better segmentation. This can be quantitatively demonstrated, yeah, in comparison with the ground truth. This example simply since it makes sense to consider and use the right noise model, not only for motion analysis, but also for segmentation. Yeah. And shape modeling is also a big issue, actually. Looking at this ultrasound, typically segmentation is based on some contour information. But look at here, there is no contour visible here. If you apply any level set whatever, you will find a contour, Hertz contour, going outside of the Hertz contour. It means we need some constraining hard model for doing this particular segmentation. And this is quite typical. And actually, unfortunately, this should be some optical flow in, and based on this shapes information and motion information, we could do a classification of the so-called hard remodeling, which segment is healthy, which segment is not healthy. But the issue here is not the classification, but the segmentation. We do need a statistical model of the herd for this segmentation problem. And another issue, another application field example is, you see, probably, I just show the video. Yeah, it's a biological application. We like to track all such larvae and find out their contour and resolve the collision. And also in this case, all the larvae, they do not show any difference in shape, in brightness, or whatever. They are very much the same. Yeah? And we needed such statistical model of the shape of this class of objects for a very reliable collision analysis. So this shows just the importance of statistical shape modeling, which is quite unique in some sense for biomedical imaging. And in today's time of machine learning, we all know we need annotation. Yeah? We need annotation for at least two purposes. One is learning. The other is for performance evaluation. Yeah? We need to compare, let's say, our segmentation results with some annotated ground truth. But in case of biomedical applications, there are some additional difficulties. Yeah? And you see here, we cannot involve anyone else than domain expert. Such internet solution as mechanical Turk is not useful in general. But the physicians, they are even more busier than us. Yeah? And also, even domain experts, they have uncertainty. For the medical annotation, we observed different physicians, they label differently. After the labeling, they cannot come to the unified opinion in some sense. And also, we have 3D database over time, 4D, of large size. So there is a lot of challenges here in case this so-called ultra microscopy with very high solution, and some domain experts, they spend several weeks for just partially annotating 2 data sets. Partially, not the whole data. This is a hard job for them. And we use such data for finding the cells, and finally the nucleus of the cells for quantification purpose. And even giving such validation data, so the question is how we validate algorithms for biomedical imaging. For instance, segmentation, motion analysis. You see here two standard approaches. We have some ground truth, for instance, for segmentation, then we just compare our automatically segmented result with such ground truth. That's fine. And also, very popular is, synthetic data. There are models for small animals, for people, and we can simulate the working of some device. Let's say, here you see here, ultrasound. Yeah? Giving such a simulation, we have ground truth for motion. For segmentation, it's fine. You can ask physicians to mass label. But can you ask a physician to specify the optical flow vectors? Nobody can do that, really. Yeah? So in this case, we have used such synthetic data. And these are very popular in general practice. But in case of medicine or biology, there is a different way, somewhere in between. So this is my colleague Klaus Schäfer's. He has built a so-called phantom. It's just a hardware body with all the organs which are controlled somehow physically, and with all the parameters of the organ movement are controlled by a software. So everything is under control in some sense. So we also use this particular form of data acquisition for algorithm validation. So these are the two standard forms of validation. This is some very specific form in medical imaging. Yeah. And so the final one, a single slide. And here is a problem very popular since maybe 20 years, retinal images. There are different databases. There are survey papers. There are hundreds of papers on this topic. And today, it's hardly possible to improve the performance measure. It's 0.99, I don't know, something. But and today, we are faced with 3D data of so-called OCT, angiography, which much poorer quality. It's much higher challenge here to deal with this kind of images compared to the classical retinal images. And these are just a few examples of challenges and some ideas, and mostly a solution from our side. I really want to emphasize the work we have done is a kind of model-based. I typically do not say we develop a solution for ultrasound. We develop a solution for PET. This is not true. Our work is motivated by ultrasound PET, but our algorithm is based on some theoretical model. As soon as some other device satisfies the same model assumption, and hopefully our algorithm will be useful for them as well. So I call it somehow model-based solutions to make our solutions as broadly applicable as possible. So talking about biomedical imaging, there is actually another aspect I've not mentioned so far, imaging. Yeah? And I have been talking about image analysis, but the question is, where do the images come from? From some device, that's true. But sometimes there is some option for developing such image acquisition techniques, and we are quite happy to have some projects in this aspect. So I like to share you two projects. One is related to biology, a very related major one. This is medicine for topic image acquisition. And One, you see here the so-called fruit flies. This is one of the most important objects for the biology study. And years ago, people started to use imaging techniques. And this is a typical setup. You have some table, you have the agar, and the larvae move above the table, above the agar sheet, and you have camera, you have lighting. And this leads to typically this kind of images with problems. You have object reflections, light refraction, whatever, and the objects look like this. And it's not very detailed imaging. For that reason, we have been working on another measurement principle. Well, basically, the principle is very simple and well known from the human computer interaction community. We have adapted it into this setup. It's based on infrared setting, and basically the light is kept within the glass and the agar. As soon as there is a larvae, the light will be reflected here in this direction, for instance, the camera. You see the table and the camera here. And I will not go to the technical details, but just show you some images. The effect here is we have extremely high contrast, basically more or less black-white, not truly black-white, but very high contrast. And this makes the segmentation tracking easier. But still, we have the tracking problem. We have the problem with the collision analysis. And actually, I have shown you as this small example with collision analysis before. Yeah. The funny thing here is, as a comparison, look at this. This is a conventional imaging technique. And there is the result from our imaging technique. And we can see through the body. We can see into the organs using this simple setup. Yeah? And this is actually the very first time it becomes possible without using a microscope. And this enables us to do investigations like studying the heartbeat pattern and to start the so-called rolling behavior on the right side. And for me, this behavior is totally not interesting. But for biologists, this is extremely interesting for them. Yeah? And we are also to deal with the different stages of the life cycle. And interesting, we can also work with the different other objects, like here, planare, C. elegans. All these larvae, fruit flies, and planare, or C. elegans, they build the body of the study objects in biology. And here is one example with plant. We are also able to measure plant. Yeah? So the next step is the most recent setup is here. And in case of this table, we still need to prepare the measurement. Take the larvae and put it on the table and measure. Yeah? So our idea, the most recent idea, is to do a long-term environment monitoring. It means we build a vial. The fruit flies, they live in the vial, and we put a number of cameras, right now 5, and observe them. Yeah? And using exactly the same principle, infrared lighting and so on and so forth, to obtain high contrast. And we are able to follow all the fruit flies for days. That's the reason why we call it film. This is the name of the technology, for days. Yeah. For a high degree of performance behavior monitoring. So indeed, let me go back. Very quickly, the second medical project about PET imaging. I have been talking about this motion compensation for patients, right? But in case of basic research, small animals are used, mouse and so forth. And you cannot ask them to be quiet for 20 minutes, never. So the standard solution is here. anesthesia. This is done worldwide many times per day in basically every lab, and with well-known problems. Yeah? So the medical people, they do know the problem related to this measurement, but there is no better solution. So we are now working on the following solution. Yeah? The best I show you is the solution. We have a chamber. We'll put the mouse into the chamber. You see on both sides there are two cameras. So you are well known with the vision, stereo vision on both sides. So we like to capture the 3D motion from both sides. And basically, what happens is you see the four cameras, two from each side. We have some markers on the fur because there are no visible features in some sense on the fur, unfortunately. And so we need to solve quite a number of computer vision challenges like high precision camera calibration and so on and so forth. Finally, what we have done is motion compensate image reconstruction. And this is a very hard job, and I'm quite happy to see the very first results after a long time of working on this project. You see a freely moving mouse for 45 minutes. This is the position of the nose tip. And here is the reconstructed image. And here is some reference. Reconstruct means freely moving, motion corrected. And this is some reference. I will not go into the details of the reference, but this reference image gives you some indication how it should look like, more or less. But this is definitely not the ground truth, I have to say. This is not the ground truth. And basically, we are able to make the first measurement using a freely moving mouse. Yeah. We are still improving this system. Hopefully, one day, we can apply it to realize improved measurement. So this is something about imaging. So challenges about image analysis, imaging acquisition. And now I'll come to say some words about machine learning. Machine learning has been used from the very beginning for biomedical imaging, actually. But today, there are some very funny applications. And here, I somehow come to one of the words in my title, potential, yeah, future. And this is one realized application, yeah, segmentation, nuclear detection. You see here, yeah, the image, here the green spots are the correctly detected ones, but you still see yellow points and red points. They mean false positive, false negative. Look at this, realized by a deep CNN, there is still quite a lot of room for further improvement, actually. And this is one example for learning features for registration. Yeah? For time reason, I will skip this slide. And actually, the next few slides, they are much more interesting from my point of view. This is some very funny project. The title is red. It means it's not from my lab, okay? But I find it so interesting. Look at this. The application here is a quantification. The physicians want to find the volume of the four parts of a heart. The heart is divided into four parts: left atrium, right atrium, and left and right ventricle. This is a quantification. Quantification is typically done by segmentation. If you have segmented well, afterwards you have imaged the volume. But the segmentation is extremely difficult here. Look at such images. How to separate the four parts. So the idea here is, okay, to avoid the segmentation. Take a picture and try to find some very nice feature representation, and then learn a function which provides four outputs for the four volumes. It's a machine learning approach for an extremely difficult segmentation problem. As said, in the history, this kind of problem was solved by segmentation. And now people are trying to solve it by learning. The next one is even more fancy. It's something for future. There's no good solution yet. And in a few months, very recent, there will be a special issue in IEEE transactional medical imaging on machine learning for image reconstruction. Yeah? And this picture was used for the call for papers. On the left side, the measured signals. On the right side, some reconstructed image. And between a neural network. This is a real challenge to all people working in applied mathematics for image reconstruction. I worked very closely with my colleagues in applied mathematics. For instance, this pet small animal moving measurement, we need to do the so-called motion compensated reconstruction. So this is not our beer. So we work together with them. Actually, I showed the colleagues there this picture, this call for paper. They are also very curious about the future development here on the one hand. On the other hand, they were also a little bit pessimistic about their own future because they were trained for totally different methods. Yeah? And so I like to cite one sentence from this great Hinton. He said 2 years ago, we should stop training radiologists right now because in 5 years, deep learning will have better performance. Yeah? Well, this is a very controversial topic, but there is substantial potential not to fully replace all the radiologists, but to work with them together towards more efficiency and so forth, and so forth. And indeed, there is this so-called AI versus doctor interactive graphic done by IEEE. It should be updated constantly, or so that you see how for general diagnostics, still the doctors win. On the other hand, there are already some topics where the doctors lose. The machine learning solutions win, and here still not decided yet. And as said, this graphic should be updated from time to time, and you can follow the most recent development of the fight between physicians and machine learning systems. And I like to, use a few minutes, or probably 2 minutes for something we are developing, a tool development, working in machine learning or deep learning, or probably some of you use this very popular library, Cafe. This is probably, particularly in academic, popular. But the problem there, it has a number of advantages, but it has some disadvantages. How to use it? Yeah? You specify your neural network in form of such text format, and you train your network using some commands and so far. It's possible to work with it, no doubt, but it's probably better or more efficient to work in a different way. And we have recently built a graphical tool, and in that tool, you can specify graphically the architecture of your network. You can import existing neural networks from such a text file. You can modify it, save it, and finally, you can start training, observe the training, and look at the trained features, a kind of visualization functions. And the basic fundamental motivation for this tool is to provide a more efficient way of prototyping deep neural networks. Not only deep, it may be not so deep. And we have used this barista system for instance, this application, you have seen this setup. The problem there is It's 4 days. After some time, there will be some dirt, quite a lot of dirt collected. Look at this. It's not so easy to distinguish between the background and the objects. This is the ground truth. This is the image after, I don't know, one day or even longer. And so we have decided CNN, not so surprising, not so deep. Why not so deep? Because we like to run it on such a microcomputer. Yeah. Okay. And indeed, we tested with, for instance, random forest. Indeed, this CNN solution provides the best performance so far. And so you are welcome to, if you are working with coffee, you are welcome to try our 2 barista. Yeah. The name barista is easy to remember, yeah, for coffee. So I just try to come to end of my talk saying some words about future. Well, it's very difficult to say something about future, but I'm quite sure the machine learning part will be further developed, applied in different variants, including how to deal with limited annotation data, yeah? And how to train such deep learning models so that we can have more understanding, so that we can provide some explanation to the physicians how our model works and so on and so forth. This is clear future direction. But from a personal point of view, actually from the environment I'm working in, I'd like to point to another issue, which is probably not so well known, so-called multi-scale imaging. I have shown you something about this ultra microscopy, and you have also seen this HERT PET imaging. This is full body scale. This is very, very fine scale, and we talk about full body scale, molecular, cellular, subcellular, nanoscale, and so on and so forth. Here, basically, you see the whole branch of scale from very fine to very coarse scale and different devices. Yeah? And the idea of multi-scale imaging is to study medical problems by involving a series of devices, not only at one scale. The idea is, for instance, to use PET at the full body scale and try to understand the mechanisms behind it. Let's say if we see something on the skin and what happened behind it by using microscopic imaging and so on and so forth. We can involve basically a number of different imaging modalities from different scales. So there is a need from a large scale to the mid-sized scale, very fine scale, and using the results back to the large scale which we can observe. Yeah? In this multi-scale imaging setup, there are quite a number of new challenges. I call them cross-scale, registration, segmentation, whatever, including visualization. And we need complex models for the relationship between the scales. Here, machine learning can be very much helpful. Yeah? And actually, this is really new. I'm citing a very new paper about registration. In this very new paper, cross-scale registration is not even mentioned. Yeah? So it produced some, and actually we should tackle such multi-scale imaging in a very interdisciplinary way. Here's just one example for looking at this disease, and we have colleagues in biochemistry. They look for the so-called marker, how to identify something. And the organic chemistry, radiochemistry, they developed the marker, probes, how to detect using chemical materials. And then we have physicians, we have biologists, we have computer scientists, and so on and so forth. Basically, we are working in such a very interdisciplinary setup, actually starting quite long ago. These research centers, let's say, This is an institute. This is a so-called cluster of excellence funded by the German government excellence initiative. Here you see about 90 research groups are working together from very different fields. Yeah? And it's not a theoretical group, a number of 90s. We indeed work very closely together. Yeah? And the next step will be something for 19. And the idea, what's the problem here? It works well, but we are distributed in different buildings, distributed over the campus. The idea is to move 10 plus something key groups into one common building so that we will see each other every day, talk to each other every day, something like that. Yeah? Okay, that's his idea. And actually, we are applying a funding for the next period, Sales Emotion 2.0. And so this is end of my talk. And basically, I've tried to discuss some specific challenges of biomedical imaging, and some shared with you some of our solutions, some solutions from other research groups. But the issue is there are specific challenges, and it's not a simple application of existing algorithms from image analysis. So I'd like to thank my collaborators and my PhD students for the results which I could share with you, and thank you for your attention.
Thank you very much.